Intanto buonasera a tutti, io mi presento, sono Luca Gammaitoni, sono professore di fisica sperimentale all'Università di Perugia, sono un fisico e sono anche il coordinatore di questo progetto Vitality, che è il progetto che ha come obiettivo la realizzazione di due poli di innovazione, uno dei grandi progetti del PNRR, quelli di cui si sente parlare spesso anche al telegiornale. È uno dei progetti in cui l'Università di Perugia è coinvolta e questo progetto in particolare ha un obiettivo che riguarda direttamente l'area di Terni, perché l'obiettivo è quello di realizzare un cosiddetto polo di innovazione, cioè un luogo dove le aziende e l'università possono collaborare insieme, e questo polo di innovazione stiamo cercando di costruirlo presso l'area del polo chimico ex Polymer. Contemporaneamente l'altro obiettivo, abbiamo due obiettivi come dicevo, uno è un polo di innovazione nella zona di Terni, l'altro è un polo di innovazione nella zona appenninica, comune di Nocera Umbra e Gualdotadino. È un progetto che dura 3 anni e che ha come obiettivo lo studio dei materiali avanzati, materiali innovativi come si dice. Qui nella zona ternana sono i cosiddetti biomateriali, cioè i materiali che hanno un'applicazione nel settore bio, cioè sono compatibili per esempio con i sistemi biologici, oppure sono originati da materiale biologico. Mentre nella zona appenninica sono i nanomateriali, una classe di materiali di cui adesso un pochino parleremo insieme al nostro ospite. Prima di presentarvi l'ospite però vorrei dare la parola al professor Gino Torre dell'Università di Perugia, che porterà i saluti a nome del polo ternano di questa università. Prego.
Grazie Luca. Noi come polo di Terni e specialmente come polo di ingegneria siamo tutti impegnati in questo progetto Vitality, anche perché non poteva non essere così, in quanto essendo un progetto strettamente dedicato ai materiali sia qui che su a Perugia, noi non potevamo starci in quanto lavoriamo sui materiali, come alcuni di voi sanno, da circa 30 anni sul polo ternano. Il polo di Terni quindi è ben felice di avere queste iniziative, in quanto fa parte della sua missione, avere persone di altissimo livello che diffondono la cultura e ci permette anche a noi di crescere ascoltando queste presentazioni e abbiamo modo di fare nuove collaborazioni, nuovi contatti e nuove storie. Fondamentalmente da noi qui al Polo, per quelli che sono di Terni, non sanno cosa facciamo, perché molto spesso succede questo. A Terni qui abbiamo il Polo di Ingegneria che è fortemente rappresentato qui da professori e da ricercatori, che lavora fondamentalmente su 2 corsi, il corso di Ingegneria industriale, la magistrale e la triennale, più il nuovo corso di ingegneria dei materiali e processi sostenibili, che quest'anno ha anche un nuovo presidente, Deborah Puglia, è qui seduta fra il pubblico, e poi il corso di ottica il triennale, che anche sta avendo molto successo in campo di studenti. Quindi il polo la parte ingegneria scientifica dal punto di vista materiali e fisica sta crescendo e speriamo che cresca ancora di più. L'ingegneria lo conoscete, medicina la conoscete tutti quanti e potrebbe anche essere interessato, non vedo rappresentanti di medicina qua che sono venuti, ma comunque questo è quanto il polo. Naturalmente mi dispiace per il professor Consigli che non è potuto venire in quanto aveva degli impegni importanti, però mi ha fatto molto piacere stare qui a presidiare questa attività con Luca.
Grazie professor Torre. Avete sentito, professor Torre ha un accento tipicamente ternano, e quindi adesso vi farò la traduzione di quello che ha detto il professor Torre. Intanto saluto il nostro amico assessore che si è unito a noi, Sergio Cardinali, che prego di venire a farci un saluto a nome del Comune di Terni, che ci ospita e siamo molto contenti. L'assessore Sergio Cardinali, prego.
Bene. Buonasera a tutti, grazie Luca. Piacere. Grande professore, questa è una città che riguarda la chimica, insomma, rispetto a premi Nobel possiamo esprimere sicuramente un'importanza molto ampia. Abbiamo anche una opportunità, credo, in questo momento in cui stiamo cercando di trovare una forma molto nuova di esprimere un'industria sostenibile che stia al passo con quello che dobbiamo affrontare nei prossimi anni, e la volontà dell'amministrazione è proprio quella di cercare di trovare una modalità, e credo che oggi vi siano tutte le opportunità e tutte le tecnologie per cui questo è possibile, per costruire intorno alla nostra città una seconda opportunità dopo 100 anni. Terni ha bisogno di rinnovarsi. Quello che ha rappresentato l'industria, le scoperte del 1900 per la nostra città sono stati una crescita sociale, crescita economica, sviluppo. Poi alla fine del secolo scorso ha iniziato a presentare questo modello di sviluppo, ha iniziato a presentare tutta la sua difficoltà, gli anni. Credo che però oggi siamo stati tutti quanti i protagonisti che in questi anni si sono impegnati per mantenere un tessuto industriale in grado ancora di accettare questa sfida, e bene abbiamo fatto. Vedo qui tanti amici e persone che hanno contribuito in questo complicato obiettivo, e credo che oggi siamo in una condizione di poter dire che da qui a qualche anno sicuramente riscriveremo ancora un'altra volta la storia di questa città. Io con il professor Gammaitoni abbiamo vissuto la stagione di Vitality per qualche anno, vissuta anche in un'altra veste, l'impegno per cercare di fare in modo che questo centro ricerca, così importante per noi, sia approdato all'interno del polo chimico, che poi in qualche momento c'è stato anche qualche idea diversa. Da questo punto di vista quindi siamo stati tutti insieme, abbiamo fatto un bel lavoro di squadra, oggi abbiamo questa opportunità, credo che nei prossimi mesi qualcosa di nuovo già farà il suo capolino all'interno del polo. Ci sono dei progetti che in questo momento sono in fase di maturazione, quindi la speranza è che poi si traducano in imprese, in lavoro e in ricerca, perché la chimica è ricerca. Quindi io vi do i migliori auguri di un buon lavoro per Vitality, anche per il prossimo impegno che l'avete impegnata nei prossimi giorni, e quindi noi con l'Università stiamo cercando di chiudere un momento di riflessione per aprirne uno completamente nuovo, e mi sembra che abbiamo messo a terra tutte le migliori condizioni, e quindi la ricerca deve essere il punto più importante per la crescita e il nuovo sviluppo di questa città. L'amministrazione c'è, e quindi i migliori auguri a tutti quanti. Grazie.
Grazie. Benissimo, siamo molto contenti di questo saluto dell'amministrazione comunale. Datemi adesso solo 2 minuti per presentare il nostro ospite di questa sera. Siamo molto onorati di ospitare qui all'Università di Perugia, in particolar modo qui a Terni, il professore Jean-Pierre Sauvage, che è premio Nobel per la chimica 2016. Professor Sauvage professor Sauvage ha fatto molti studi, ha studiato inizialmente a Parigi, poi si è spostato in giro per il mondo, attualmente è professore emerito a Strasburgo, all'Università di Strasburgo, e ha dato un contributo fondamentale che adesso provo a riassumere brevemente allo sviluppo della chimica, motivo per cui insieme a altri due colleghi di cui poi lui ci parlerà ha avuto il riconoscimento del premio Nobel, che è un premio estremamente prestigioso. Voi sapete che a volte viene fatto risalire la nascita della civiltà moderna in realtà all'apparire delle macchine. La nostra è chiaramente una civiltà delle macchine. E le prime macchine sono quelle che potete facilmente immaginare, la leva, la ruota. Queste sono invenzioni, oggetti che non esistevano in natura, che sono stati inventati per eseguire dei compiti. Quindi l'invenzione delle macchine ha portato uno sviluppo enorme. Ecco, quello a cui ha dato un contributo importantissimo il professor Sauvage è proprio l'invenzione di queste macchine a una scala molto più piccola. Pensate alla possibilità di costruire macchine così piccole da poter essere inserite per esempio all'interno del corpo umano, macchine che possono essere in grado di riparare le nostre cellule, oppure di curare malattie che oggi non sono curabili, di intervenire sul DNA di alcune cellule per riparare dei difetti genetici. Veramente la possibilità di costruire macchine a dimensioni nanoscopiche, cioè di pochi nanometri, dove un nanometro vuole dire 1/1000 di metro. Pensate a un macchinario di quelli quelli che vediamo qui per esempio, e lo rimpiccolite di 1 miliardo di volte. Un macchinario così fatto non esiste in natura, così come non esistono questi macchinari, ma può essere costruito. Ecco, il contributo che ha dato il professor Sauvage con i suoi collaboratori è indicarci la strada su come costruire queste macchine. Sono macchine di dimensioni molecolari, fatte a volte di pochi atomi. Ecco, il suo contributo, che è importantissimo, avrà sviluppi e conseguenze pratiche che noi scopriremo da qui ai prossimi 50 anni. E chi avrà la possibilità di vivere così a lungo, e ci sono sicuramente qui persone che sono candidate a questo, vedranno e diranno: io quella volta c'ero quando il professor Sauvage è venuto a Terni e ci ha raccontato come è iniziata questa storia. È veramente una storia molto entusiasmante e molto eccitante, e per noi è un privilegio avere la possibilità di ospitare il professor Sauvage qui all'Università di Perugia. Quindi, senza ulteriore indugio, io lascio la parola a lui. Vi dico che la lezione sarà tenuta in inglese, ma le slide sono in italiano, quindi sono facilmente leggibili. Inoltre il professor Sauvage parla anche l'italiano, quindi poi dopo, alla fine, se volete, ci sarà uno spazio per fare delle domande, e se volete fare domande le potete fare sia in inglese che in italiano. L'inglese è la lingua naturale, la lingua franca della scienza, quindi è normale anche per tutti noi che facciamo questo mestiere tenere dei seminari come questo in inglese, però il dialogo e la conversazione lo potremo fare anche in italiano se volete. Senza ulteriore indugio lascio la parola al professor Jean-Pierre Sauvage. Grazie.
Grazie Luca. Merci. Buonasera a tutti. Mi dispiace, ma non sono capace di dare la mia conferenza in italiano. E come le sapete, in scienza la tradizione è di parlare in inglese, allora parlo in inglese. So first I would like to thank you for inviting me here in this city, which I didn't know, and which is of course a very important city in many respects, industrially and economically. And I would like to again thank Professor Gammaitoni for arranging everything. He's the very best host you can think of, honestly, Luca. And I will start my lecture as soon as I have the first slide, and here it is. So we're going to talk about artificial, So again, I have a problem with the laser. Okay. So we will talk about molecular machines, molecular motors at the molecular level. And we will start with a bit of chemistry. I'm sure that most of you are relatively familiar with molecules, but maybe some of them do not remember exactly what a molecule is. And so for a few minutes, it's going to be a kind of a lesson in the molecular sciences. So molecules are assemblies of atoms. Atoms, you can find all the atoms existing in the universe in a big table, which is the periodic table or the Mendeleev table. Some of you might remember that. But I just took a few examples. So if you have water, H2O, you have an oxygen atom at the center and two hydrogen atoms laterally with a given angles between those chemical bonds. So the white lines here are chemical bonds. Carbonic anhydrate, CO2, has a very nasty reputation. Of course, it participates in the pollution processes, and this is very serious. But I think we should also keep in mind that it is absolutely indispensable for photosynthesis. So we rely on plants, we rely on green plants, and green plants function thanks to CO2, light and CO2. So let's get rid of CO2, but not too much. Oxygen, two wide bonds, here and here. So this is a very stable molecule, because if you have two bonds between two atoms, it means that the molecule you obtain is very stable. And probably the most stable molecule you can think of is dinitrogen, N2. So N2 is about 80% of our atmosphere, and N2 is basically an indestructible, non-destructible molecule. And N2 has been converted to ammonia many, many years ago by beautiful processes, including Italian work. But you need a lot of energy to break the triple bond of NN. Another molecule which I like particularly is a phthalocyanine. And I'm sure you heard of phthalocyanines. Have you? The name, maybe it's not so common. Phthalocyanine, it's a dye. It's probably the most important industrial dye. And in particular, if you take copper phthalocyanine, the molecule which is represented here, most of the inks, blue inks, are based on this molecule. It's a nice-looking molecule because of the symmetry. And on top of that, it's a very, very stable species. So now, a bit of chemistry, elemental chemistry. If you look at these vertices here, so here you have a hexagon and vertices. And this means that you have 6 carbon atoms arranged as a hexagon, plus a certain number of hydrogen atoms to make the system very stable. Just to remind you, we do not draw the atoms anymore. Normally here, you should have a C for carbon, but we have to assume that it's totally useless to draw a C, the C letter. So by convention, everything which has no letter is a carbon atom. I would like now to show you an interesting example of the molecular sciences. So many years ago, maybe 30 years ago or 40 years ago, chemists were interested in molecules which are very abundant in space, intersideral space between the stars, and you have a lot of molecules, many, many molecules. Of course, the molecules are diluted, but if you try to make a summation, you will find a huge amount of molecules in space. And the people were trying to reproduce what could have produced these molecules in a laboratory. So they did something nice. They took some graphite, carbon, graphite, and they bombarded graphite with very energetical photons, so a laser, very powerful laser, to see what was going on. They never found the molecules you find in space, but they found a very interesting molecule, which is pure carbon. So here you have 60 carbon atoms assembled exactly as a soccer ball. So if you look at a classical soccer ball here, you will find also 60 vertices. And so C60 was found, and it has fantastic properties. So this led to a Nobel Prize. And I use this example to remind you of the size of the nanometer. So here, a nanometer, this is exactly the size of this species. Going from here to here, it's 1 nanometer. And the nanometer, we know that it's 10 to the minus 9 meters, but I think it's important to realize what it means. So the nanometer to the meter, there is a ratio, 10 to the 9th, is exactly the same as the ratio between a small bar, let's say 30 centimeters bar, and the distance between Earth and Moon. So it's really, the nanometer, when we say it's a very tiny species, it's true. Now, a very important statement. If you look at the many molecules which have been made by chemists, do you have any idea of how many molecules have been made in chemistry, artificial molecules? It's probably something like 10 million molecules, so really a very large number of molecules. And if you look at these molecules, we say synthetic molecules, everybody will agree that they are kind of motionless, or we have no control over the way they move. They are not really motionless, they can vibrate, distort, but all the motions are stochastic, which means due to random, no control over those motions. And this is really a general property for molecules made by chemists. Now, let's look at the other family of molecules, which is exceedingly important, the biological molecules. And for biological molecules, the situation is totally different. Motion is extremely important, and in particular, controlled motion. And we will see 1 or 2 examples of molecules, biological molecules, which move in a very precisely defined way. And those species are biological molecular machines or biological molecular motors. And so some biological motors can walk, some others can rotate, some others can contract, elongate, and all that is very strictly controlled in the biological medium. So these species are called motor proteins or proteinae motoriae. I will show you 2 examples briefly, because I'm a chemist and I prefer to talk about chemistry rather than about biology. But we will take just 2 simple examples. I think, if you are not so much aware of chemical biology, you just, think of whatever you like. But ATP synthase it's an enzyme. It's an enzyme which is everywhere. It's in your body, in my body. It's in the body of everything which lives on Earth. The most primitive bacteria, to mammals, to human beings, contain ATPase or ATP synthase, this enzyme. And this enzyme, without entering the details, is responsible for handling energy. So this enzyme can make our fuel. Our fuel is ATP, but this is not essential. And this enzyme can also burn ATP. Burning is not the right word, but it's by analogy to fuel, to gas, or gasoline. And so this fuel will be burnt when our body needs energy. All that occurs at a cellular level. So again, very, very tiny species. And the beauty of ATP synthase is that it's a rotary motor. So now we take a cell, and in our body there are billions of cells, and you take a cell, and on a membrane, again, on the membrane here of the cell, there is this enzyme, this ATP synthase, which has been embedded. And this enzyme will function as an ATP maker, synthesizer of the fuel. So we will not have much time to talk about all the details. It's a very complicated process. But what you have to remember, just this enzyme is a rotary motor. So you see the rotor at the center here, the rotor, and as the rotor rotates, ATP, the fuel, is made out of degraded molecules. This is very important, of course. And just for you to have an image, ATP, which is the fuel of life, you have to make it all the time. And in average, everyone here in this room makes about 1/2 of their weight of ATP every day. So I make something like 40 kilos of ATP every day. And we can easily calculate for you. I insist on that, it's not a minor process. So this is probably the most important rotary motor on Earth. Without it, no life. Another example, which is also very spectacular, is the kinesin. So you know that we have cells. Again, I come back to our cells. And in the cell, you have a lot of things happening. And in particular, you have factories, biofactories, making pieces of DNA, making small pieces of proteins, making hormones, and all kind of complex and very important biological molecules. But these molecules have to be dispatched and go from the biosynthetic system, company, let's say, or factory, to other places in the cell. So the cell is huge. It's 1 micron, very, very large compared to the nanometer. And then you have an enzyme which consists in transporting the molecules which have been made at some point in the cell, and then dispatching them, transporting them to where they are needed. And this is the enzyme. Kinesin, it's this little thing here, which walks. It's a walker, exactly like a walker you find in the mountains from time to time. It walks. And at the back of the kinesin, which is that, you have a huge bag. And this huge bag contains the molecules which have been made somewhere, but which have been transported to some other places in the cell. It's a fantastic enzyme, able to walk. I have a question for you, by the way. Do you think this enzyme is alive? No, it's not alive. It's simply a complex molecular systems which we can even isolate, study, and put back in a living medium, but of course it's not alive. So the statement, another statement, chemists, most of the time, or let's say organic chemists, are fascinated by biology. And so they like to look at the structures found in biology, and perhaps also they like to imitate, to get inspired by biology and imitate biological systems, both from the structural viewpoint to the functions. And in order to do that, a family of molecules has been used extensively in the last 30 years or so. So these molecules contain rings, anelli. And so we have here a system, a molecule, which is a catenane in English, or catenano in Italian. This is the simplest catenane. You have two interlocking rings. But these molecules were considered as impossible to make. Many people have tried, but it was a failure each time. And another molecule, which is somewhat related to the first one, is a rotaxane. You have a wheel, rota, in Latin, as you know better than I, and the wheel, the rota, has been threaded by an axis. So it gives the word rotaxane. So the first question you may address is, why are catenanes and rotaxanes interesting in relation to motion and to molecular machines and molecular motors? This is the question addressed here. So, very simple. If you have catenanes or rotaxanes, you can imagine that these systems might be set in motion by sending a signal to the molecules, and thus you would have interesting molecular machines in motion, such as this one. So the ring can glide from one spot to another spot here. So you will have a linear motor, very similar to a piston moving in a cylinder, very similar. Here you will have some kind of rotary machine. Another example here. In a catenane, a ring can be fixed and another can rotate within the first ring. And thus, these systems seem to be very well adapted to making molecular motors and molecular machines. And I will now switch completely to another field. Sometimes, you can work in a given field, you can be very productive, but jumping from a field to another field can also lead you to very novel, original data. And I think this is what happened to us. So many years ago, with my boss of the time, Jean-Marie Lehn, we had been working on a big project which was trying to split the water molecule to H2 and 1/2 O2. Why is it exciting? Why that, in your opinion? Because H2 is the ideal fuel. And so if you can split the water molecule using, for example, solar energy, it will be a big thing. You can produce H2 basically for free using light and water. Water doesn't cost anything, light doesn't cost too much, and you would obtain dihydrogen, the ideal fuel. But this is still kind of a dream. And when many groups were trying to do that, they were using a very special molecule, which we call a complex. Complex because it assembles organic fragments like this one, and the third one, and a transition metal, a metal which is in this case ruthenium. So ruthenium, if you look in the periodic table, it is just below iron. So this complex was really fantastic with all the needed properties for splitting the water molecule. But there was a big problem. Ruthenium is very similar to gold, rhodium, platinum. It's a rare metal, a noble metal, so extremely expensive and extremely rare. So when we entered the field, we had in mind that ruthenium should be replaced one day by another metal, and copper seemed to be very well adapted. So we started a collaboration with an American friend, David McMillan, who was working at Purdue University in Indiana, in the US. We knew each other for some time. And David McMillan visited Strasbourg. He spent a year in Strasbourg. And it was a great moment because we could collaborate, exchange ideas, and start really new work combining synthesis, organic synthesis, that was our field, and photochemistry and photophysics, and that was his field, Dave McMillan's field. So we had made this molecule, relatively simple molecule, and when Dave McMillan saw this molecule, he got very excited. And he told us to add a little bit of copper, and you will obtain a new species which will be very interesting from the photochemistry and photophysics viewpoint. And this is what we did. We made the complex, so this is called a complex again, and this complex had interesting photochemical properties, but it was not the most important. So now if we materialize the endpoints of the various fragments. So here we have, let's say, the vertical fragment. Here we have the horizontal fragment. And the vertical fragment contains two endpoints, two extremities, which have been colored in blue. So this is for the vertical fragment. And the horizontal fragment, we can easily materialize the endpoints with red balls here. And now, in terms of strategy, we realized that if we interlink the two blue dots and separately the two red dots, we obtain something of interest. What do we obtain? Yes, we obtain a catenane. And so that was very simple. It seemed to be very simple. We obtain a ring here containing the red fragment and another ring here containing the blue fragment. And those two rings are married forever. No way you can separate them except if you cleave a chemical bond and unthread one of the fragments. And so we decided that maybe we should stop what we were doing before and try to make catenanes. And again, it was kind of a virgin field. Catenanes had not been made, and we thus decided to change completely our research field and to jump towards catenanes and related species. So this is something I would like to stress. Catenane had never been made, let's say, in preparative quantities, and thus we thought it was really timely to make catenanes, grams of catenanes or even more, and show that they can be used for various applications. So I'm sorry, I think there was some confusion in my slides. So I show you the strategy. We start from these species, whose formula is shown here. And we will make a catenane using a strategy. We call it strategy A. We take a copper ion, copper 1+, copper ion, and we mix. Copper 1, we obtain this kind of species, and now we cyclize, go make a ring on the right, make a ring on the left, and we have a catenane. So that was really the simplest strategy we could think of, and it turned out to be extremely efficient. And the other strategy would be to start from a ring, which we have made separately, and now we will use copper, attract a second fragment, and finally cyclize. Copper and the cycle. And we obtain the same species, but we have two different strategies. So we published many years ago the synthesis of a catenane, so that was the first time that chemists could make grams and grams of catenanes. I think the chemistry community liked it. And I would like to thank Dr. Dietrich Büchecker, the lady who did the work, who was a research director in our CNR, CNRS, which is a bit similar to the Italian CNR. So let me now talk about the very first catenane in motion, which we have made and studied. And I think it was also important for the field of molecular machines and molecular motor. So we start from this species. So we have copper 1 here, and we will abstract an electron from copper 1 and go to copper 2+ here. And copper 2+ has something very special. It likes to be surrounded by 4 nitrogen atoms. So here we have our nitrogen atoms. And if you are here, you generate an unstable species. The molecule wants to rearrange. It's totally unhappy. And the only thing it can do, which will be very satisfactory for its good health, is to rotate the ring, which is here, so as to replace the 2 nitrogen atoms which were originally here by the 3 nitrogen atoms which are here. So this spins. You generate a very stable species now. Everybody is smiley. And you can go back. You inject an electron in a copper 2+ species. You generate a very unstable species because copper 2+ hates so from 2+ to 1+, and 1+ hates to be coordinated or interacting with 5 nitrogen atoms. And finally, it rotates, and you regenerate the starting form. I think it's probably much easier to visualize on a video. Copper 1 to copper 2+, the system moves, you obtain a stable species, you can inject an electron, it will go back to the previous shape, previous structure. So I'm sure everybody has some, I'm not sure everybody can understand all the details, but it gives you an idea of what a pirouetting molecular machine is. So let me talk about some work which was done in Japan already many years ago, but which is very significant, and it contributed to the field of molecular machines in a very significant way. So the signal will not be electrons abstracting an electron or injecting an electron. It will be a photon. Now we will work with photons. And there is a very old reaction which has been used by chemists from time to time, which is the photochemical conversion of azobenzene. So this is azobenzene, but it's not important. But this is the geometry you have, trans, like that. And if you shine light on it, UV, you go from here to here, cis, in the same direction. And you can go back if you heat a bit or if you use light, different light. So this was really a very important reaction, which has been more or less forgotten for I don't know, 20 years, 30 years, even more, and which has been used in a very clever way by Japanese scientists. And this is a very nice example, I believe, the work of Shinkai and his group. If you take this azobenzene, so this is the molecule we have just seen, this form here. If you take azobenzene here, you have the cis form, so let's say like this, or you have the trans form like that. If you start from here, you have a positive charge. You see the plus here. And the positive charge can interact with this ring here. You have a ring of 6 oxygen atoms, and the positive charge should be able to interact. But if you have this shape, there is no way. The distance is too large for this species interacting with the ring which is here. Now you shine light, you photo-excite the system, you generate the other form, the cis form, with now the two groups coming to close proximity, and you may have this kind of interaction with the positive charge, which is here at the end of the filament, so to say, now interacting with the ring. And this is a very nice system. It is reversible, so you modify completely the shape, and in addition, you modify the properties because you have something which cannot interact with the positive charge here, which you convert in something which has a strong interaction with the positive charge. Now I will show you something which is really historical, very, very important. This is the work of Feringa and his co-workers in the north of the Netherlands, in Groningen. And these people have been using photonic signals, light, UV light, most of the time. Now you start from this species. No need to look at all the details, but you see here you have a C-C double bond. And a C-C double bond can react photochemically when you shine light on it. You can modify its shape very, very strongly, very efficiently. And so you go from here to here. Now you wait a little bit, so the system continues to rotate. So the third form will be this one. Again, you shine light, and you generate the fourth form, the fourth shape, and finally you heat a little bit and you go back here. In my opinion, the slide here cannot be understood. It doesn't speak to you except if you are a highly specialized chemist. Let me show you a video. You will see it much better, I'm sure. So this is the molecule, the same as the one we have seen before. You have a double bond here. You see, C-C. And this double bond, when you shine light on it, will react, will modify its shape, and you will have two photonic signals and two thermal signals. So let's look at that. We can also relax, it's already, we have spoken for some time. So do you identify your rotary motor? Can you see there is a rotation? Flash, it rotates. Heating, flash, it rotates. Can you visualize the motion? I hope you can. If you cannot, I'm very sorry to say that I cannot help you. It's a rotary motor, you know. So that was very important. Rotary motors have been used since the very first rotary motor was made in many, many very sophisticated systems, even liquid crystals and solids, and even they made a nano car, you know, a car which can be set in motion on a surface, nano car, so very, very tiny car. And I'm now going to talk about another example, which is also very exciting, una navetta, so a shuttle in English. And a shuttle, simple again, you have a ring, it will be, it goes from the green station to the red station, and it can come back. And it can do that many, many times. It's a very clean system, and it has been used in a very spectacular application, which is molecular computing. I'll show you. So this is a very simple thing. You have the blue ring here, positively charged, which can go from the red station to the green station, and vice versa, go back from the green station to the red station, just playing with electrons. You inject an electron or you inject a positive charge. I would like to pay homage to Professor Vincenzo Balzani all'Università di Bologna. And Vincenzo Balzani played a very, very important role in the field of molecular machines. He collaborated extensively with Fraser Stoddart, one of the 3 laureates, and many people believe that he would have deserved the Nobel Prize if let's say, the Nobel Prize administration had been a little bit more flexible, but you can never be more than 3 people receiving the same Nobel Prize. But I would like again to say that he's a highly respected scientist, and everybody would have been very happy if he had been awarded. So just to show you again some application by the group of Stoddart. So they made an electronic memory storing device, very much based on what we saw before. You have a ring here which can move from here to here, from the green station to the red station. This is very, very clean. And now if you attach both extremities on nano electrodes, and so with the nano electrodes you can inject an electron or inject a negative charge, and this will lead to motion of the ring. Now, depending on whether the ring is sitting here or sitting on the other station, the electronic conductivity of a bundle of such molecules varies, and you can very easily, by conduction measurements, know whether the ring is here or on the red station. If you apply a reasonably strong potential, all the rings will go back to the initial position on the green station, so that you have write by applying a potential, moving the ring, read, because electronic conduction will be different depending on where the ring is sitting, and finally erase. And this is exactly the principle for storing energy, storing information, And this has been used, they made some electronic memory storage device. Everybody applauded, everybody was very excited. Hewlett-Packard gave a lot of money to these people, but very unfortunately, molecules are fragile. So once you have done maybe 500 cycles or 1,000 cycles, the molecules complain, which means some of them are degraded, and so the project was kind of stopped. But in principle, I think it's a very beautiful project. So let me talk about the very last system, if I'm, I don't know, I still have a few minutes. So this is a molecular muscle. So chemists, have made many things, and one of the systems which was made relatively popular was making a molecular muscle, so a system which can contract or elongate at will when you send a chemical signal to it, and this is very similar to our muscles, the striated muscles. So you need a source of energy, and our source of energy was a chemical, and so this is what we did. We could contract the system from 8 nanometers to 6 nanometers, and I think the beauty of the system is that it functions a little bit like our muscles. Our muscles are not at all springs. You do not contract them in a very aggressive way, so to say, but you have filaments which glide along one another, myosin and actin, the thin filaments, and myosin, the thick filaments. And this one, I think, was a nice example of gliding filaments leading to elongation or contraction. I will finish up with something apparently spectacular. So recently, some people were very inspired by the work of Feringa, the photochemically driven rotary motor, and they decided to make a trapano molecolare. And so it's a drill, or perceuse in French, drill in English. So here you have the drill. So if you irradiate this molecule, this double bond here will start rotating. So this fragment will rotate like that. And now if you have a membrane in close proximity, you can drill a hole. And what they did was very clever. So they attached 2 very polar fragments, and those positively charged fragments can interact with the membrane of a cell. And they, to be even more spectacular, they took pancreatic cancer cells. Pancreas cancer is a very nasty thing. They took pancreatic cancer cells. They took the molecule, either molecule number 1 or molecule number 2, and they irradiated, with light. And so the drill, was coming close to the membrane of the cell, attaching itself via those 2 extremities, and then by shining light, it was drilling a hole, and that was killing the cell, of course. But, I think it's a very nice example, but there is a problem. So this is in vitro. In a flask, you have cancer cells, or you have other types of cells, no interference with other molecules. But if you want now to work in vivo, it will be, of course, totally different, because you will have lots of other things, proteins, hormones, many other molecules, and these molecules will interfere with the drill, and so we have still, to be very quiet, very careful. There is, a long distance between in vitro studies and in vivo, in medicine, in vivo studies. So let me finish up by thanking the people who did the work in my group. We had a fantastic team of people, And I think this is the strength of the CNRS, the French CNRS, which is to combine professional researchers and professors within the same team with postdocs and PhD students. And really I'm very grateful to these people. Let me thank my university, the French CNRS, the European community, so they were very generous to us. The ISIS, the last institute in which I worked, and I'm still working in this institute, ISIS, Northwestern University near Chicago, where I spent 3 years commuting between Strasbourg and Chicago. That was a great time. My former boss, Jean-Marie Lehn, who won the Nobel Prize in 1987, at a very young age for this kind of recognition. Malcolm Green, my supervisor when I was a postdoc in Oxford, in the UK. 2 teachers, my family, and my 2 good friends, Professor Stoddert and then Feringa. And I think this is just to show you a picture taken in Stockholm when we received the Nobel Prize, Ben Feringa, Professor Stoddert, and I. And I think the committee in Stockholm was very surprised that we were apparently very close friends. And many times, when there are 3 Nobel Prize laureates winning the prize, there are some tensions because one is jealous of something. It may happen, let's say. But we never had any problem, any tension. Thank you so much for your attention.
Okay. So thank you so much, Jean-Pierre. It was very beautiful indeed. Adesso abbiamo spazio, tempo per qualche domanda. Le domande possono essere fatte in italiano o in inglese, come volete. Mentre ci pensate un secondo, vorrei chiedere al professor Fausto Elisei, che è il prorettore dell'Università degli Studi di Perugia, che si è unito a noi, di portare un saluto a nome del rettore e suo per l'Università di Perugia. Grazie Fausto.
To everybody. It's a pleasure to stay here. I'm sorry I was late, a little bit late for traffic, and that I arrived after the beginning of the meeting. It was wonderful, also from my point of view, because we study this kind of things with light. So I'm a photochemist of organic substrates, so I can appreciate very much your work. You're working the time, long time. And what the young people needs is people with experience, which is able to push, to give idea, and to have the opportunity to improve their activity. So it's very important. I thank very much Luca Gammaitoni that within the program, the project Vitality, was able to bring a lot of people of interest from the research point of view. So, in my opinion, the academic of Perugia had the opportunity to increase, to improve their ability. So, thank you very much. Thank you to everybody for your stay here, and we're waiting for your questions. Thank you.
Grazie. E adesso, se volete, c'è spazio per qualche domanda. Abbiamo un microfono di questi portatili, quindi alzate pure la mano. C'è il professor Torre qui. Prego.
Thanks a lot for the presentation, it was fantastic. I was curious about the time scale of this movement. For example, when you saw the stereo shuttle that was going from one side to the other, what was the time scale? What was the speed?
Yeah, no, I get the point. Let me tell you, at the very beginning, it was moving in a very slow fashion. You know. The time scale was, let's say, seconds or 10 seconds. And as it is very often the case, you know, when you observe the molecules you are working with, you recognize that the system can be improved by modifying the substituent, adding a substituent here, removing another one, etc. And within maybe 5 or 6 years, we could convert the seconds into microseconds. So they can move in microseconds. But the systems of Feringa are much, much faster to respond to light. And at the beginning, you know, when they started, they published their first paper in 1999 with the light-driven molecular motor. And at the beginning, it used to take them one afternoon to perform one turn. And nowadays, they are between the nanosecond and the microsecond. Yeah.
So it's just tune.
Yeah, tune. I mean, modifying the substituents, you know, understanding what inhibits the system from being very fast, and then replacing substituents by others. Yeah.
Thanks.
Thank you. Very important question.
Grazie, quindi la domanda sui tempi, sulla scala dei tempi. Prego.
Thank you. I'm Francesco Fantozzi. I'm a professor of turbo machinery and energy systems. So I was very intrigued by the title of your presentation on machines. And I was wondering what would be the perspectives to scale up from nanoscale to actual scale, from nanometers to meters, and maybe some application on energy storage, for example.
Yeah.
Can you say something on that? Thank you.
Yeah, thank you for the question. I think, you know, the field is still in its infancy in terms of applications. The people are very happy, you know, they made funny molecules, but in terms of applications, I can say that, you know, some other groups than us made filaments, you know, filaments which can be elongated or contracted by changing the pH. They are micrometer. Many people work in the field I discussed at the very end of my lecture, you know, trying to kill cancer cells in vivo. I'm afraid there is still, you know, a long period of research to be waited for, you know, before we can obtain results. There is another field which I mentioned, which is storing information, storing and processing information. But again, I do not believe that with the systems we have for the moment, sorry, we will find important applications in the next 2 years or so. So it's a long-term perspective, I'm afraid.
Grazie. Giustamente il professor Fantozzi è interessato alle applicazioni, ci ha fatto vedere, ha dato un numero che sono 10 alla 11 bit per centimetro quadrato, sono circa 100 gigabit di memoria centimetro quadrato, che è un numero, diciamo, molto interessante dal punto di vista applicativo. Bene, altre domande? Prego.
Thank you for your presentation, and I just want to ask, what is the analytical method to see this molecular motion? How did you appreciate it?
Yeah, very good point. There are several techniques. In our case, if we have copper 1 and copper 2, we can easily estimate very precisely what is the surrounding of the copper if we have 5 nitrogen atoms, if we have 4 nitrogen atoms, if we have less. And this gives you a very precise image of what you obtain and what you start from. So we know exactly what we obtain, you know, after starting from a 4-coordinate complex, we know where we go. Of course, we have NMR, you know, but not with copper-2. The people have been using STM on surfaces, scanning, tunneling microscopy. So there is a set of techniques which can be used. And yeah, that's all. Yeah.
Grazie. Altre domande? Si accettano domande anche in italiano, quindi non vi fate problemi. Avete sentito prima all'inizio che il professor Sauvage può parlare un ottimo italiano. Prego.
You asked questions in English, so now in Italian should be easier.
Bene. Se non ci sono, te ne faccio una io, una domanda in italiano questa.
Sì, ok, proviamo.
E riguarda una cosa che molte persone, io all'inizio ho anticipato, sicuramente ci sono applicazioni, no? Nel settore dell'energia, nel settore dell'informazione, che sono interessanti, ma dove la curiosità di molti va è nel settore biologico. Cioè, io ho detto all'inizio, questo è the very beginning, l'inizio di un percorso lungo che può durare anche 50 o 100 anni.
Sì.
Nella tua impressione, nella tua immaginazione, sarà possibile sostituire ai farmaci, le medicine che usiamo oggi, delle macchine molecolari, cioè qualcosa che non funzioni semplicemente alla cieca come fa un farmaco spesso, ma che abbia in sé uno scopo, una direzione, una, tra virgolette, volontà nel cercare, nel curare una malattia. Quindi diciamo micro robot, nano robot.
Some people, you know, I answer in English. Some people, you know, claim that one day we will have micro robots able to reach cancer cells. I think this is very realistic, you know, because of antibody techniques to get close to a cancer cell and then deliver a molecule which will kill the cancer cell. And I know there is already some work, you know, very serious work done with this idea, you know, trying to find the cancer cells and kill them.
Okay. When you say this, quando tu dici questa cosa, molte persone si preoccupano e pensano che questo sia un futuro molto preoccupante perché andiamo a modificare l'organismo umano, andiamo a intervenire su aspetti molto... Dobbiamo preoccuparci oppure no?
My feeling is that we can have molecular systems, you know, acting as motors and injecting a poison close to the cancer cell, but those molecules will not live forever. You know, especially in a living medium, you know, you have a lot of aggressors, so to say, which can destroy these molecules. So it will be a, you know, a very subtle definition of the time scale for the life of these machines. Yeah.
Grazie. Prego, c'è una domanda laggiù.
Of course, the medicine perspective is really interesting, but from a pure, like, chemical aspect, what is, like, the next molecule, like the next thing that you can think of and you can do it yet, and you want to create, like, the next motor, the next?
You know, I didn't talk about the very last system we made, which is a compressor. So you take a molecule, and you have two plates, you send a signal, you contract the molecule, And so we liked it because it's very bio-like. You know, there are biological systems which repair proteins, which act exactly like that, you know, by massaging, you know, massage the proteins. Something which I'm sure will be used will be transporting molecules across a membrane. You know, this is still very difficult. You need transporters. And I think some molecular machines, in my opinion, in the future, will attach themselves or complex the molecule to be transported and then go through the membrane and release the transporting molecule. So I believe very much in that, you know, transporting molecules or even ions through a membrane.
Grazie, molto molto interessante. Prego, c'è una domanda laggiù?
Sì, non mi occupo di scienza stricto sensu, però lavoro nell'ambito della filosofia della scienza, che mi sembra una disciplina affine e molto attinente su quanto detto. E mi ricollego un po' alla domanda, alla tematica sollevata dal professore e chiedo se è stata, sicuramente sì, insomma, presa in considerazione una relazione con l'intelligenza artificiale, perché da questo punto di vista potremmo, ovviamente a lunga gittata, aver trovato la macchina per l'immortalità, insomma.
I need your help.
It's about never-ending life. Is this the path to never-ending life if we combine artificial intelligence with this molecular?
Never-ending life.
Right. Immortality.
See, yeah, I got it. I don't know, this is not a live system, you know, it doesn't live. The system we are making are inert molecular systems. They can be very stable, but I think it's very difficult to imagine that someday, you know, it can make, let's say, living systems immortal. I don't know how.
Well, the question is about actually about philosophy of science. Is this a path toward that? Certainly, there is an effort to prolongate life, of course.
Yeah, sure.
This is typical of medicine, and there is also this subtle difference between what is alive and what is not alive.
Yeah.
When you scale down to nanomechanical systems, it's very difficult to see. I mean, still at nanoscale, life is something which is much, much bigger.
Of course.
A cell is something that is huge compared to the kind of motor that we are dealing with. But certainly the combination of artificial intelligence and this kind of machinery can help to prolongate or to cure a number of illness.
But you know, there is something which can be confusing. I show some videos, you know, regularly in my lectures, and some people might believe that the systems that move, that walk or whatever, are alive. No, they are simple molecules, or let's say complicated molecules, but much simpler than a living organism. And just to take an example, you know, the kinesin, which is the walker, you can extract it like a normal synthetic molecule. You can extract it, you can deposit it on a surface, and you can put some ATP or whatever, and it will walk. You know, it doesn't think of anything. It's a synthetic system, very much like a synthetic system. So maybe those molecules will help prolong life under good conditions, but they are not at all alive themselves.
Non sono molto più vive di un topolino meccanico che noi carichiamo, molla e poi va, diciamo. Però questa è un po' l'idea che c'è dietro. Grazie. Ci sono altre domande? Prego.
So,
can you stand up, please? Because we don't see you.
Yeah.
So I'm just a student, just to say, and I just follow this chemistry at advanced levels just for a hobby, so maybe there are a few things that I'm misunderstanding because I'm not a professional. So, regarding this discovery and its potential applications in various fields, I was very curious if you could provide any insights regarding its application in aerospatial exploration.
Exploration in which exploration in which context?
So.
Sorry.
Just to.
Okay. Space exploration.
Oh, space exploration.
Okay, I didn't get it. Yeah.
If you could provide any video.
I think there is still, a bit of time to wait before these molecules are going to go to space. But that's a good idea, because one knows the behavior of these molecular systems on Earth, but in space it could be totally different. Yeah, sure, it's an interesting problem. Yeah.
Bene, abbiamo una domanda qui, prego.
Allora, noi sappiamo che ogni farmaco che prendiamo è un xenobiotico, xenobiotic. Every drug we take, it's a xenobiotic in our body. So the body works in order to destroy everything we take, also if it's a drug and it's good for us. I don't know if this question is strange, but in your opinion, if this system we take works like a drug, they will be destroyed before they take an action, or they work good.
So it's about antibiotics. I'm sorry, I missed the last part. So it says that when you take antibiotics, you have secondary effect. Is this what you mean?
La domanda sarebbe se questi sistemi lavorano o vengono distrutti ancora prima che entra nel nostro organismo, visto che comunque sono agenti estranei e vengono dal nostro organismo. Comunque lavora per distruggerli.
Yes, this is something that you mentioned before. These molecular motors basically are extraneous bodies.
Yeah,
and then when you inject them into the biological system, they are attacked by all kind of.
Yeah, of course. Yeah. I think there are ways to protect them. There are some functional groups which are very resistant in terms of traveling in the body. Fluorinated species, and very resistant.
So they will be destroyed in the liver as all drugs.
Yeah.
We don't know because.
Probably you're right. In the liver, very few molecules survive. Yeah, I agree.
Which is a good news.
Yeah, which is good. It's reassuring.
Ok. Bene, ci sono altre domande? Se non ci sono, io direi che siamo arrivati alla fine della serata. Ringraziamo di nuovo il professor Jean-Pierre Sauvage.